Okay, let's get started. All right, today we are happy to have Thomas Grimm. Please take it away.
Okay, well, yeah, thanks. Thanks for inviting me to give this talk here. And this talk will actually be about Tame geometry in quantum field theories and string theory, so string theory effective actions in particular. It is based, well, it originally started with a paper with three brilliant mathematicians, which are Ben Bakker, Christian Schnell, and Jakob Zimmermann. And well, initiated by this paper, I started, or by the work on this paper, I started to think a bit more about tame geometry and tameness in physics, and which then was summarized in this paper in some sort of context of a tameness conjecture. And in the next few months, we have several projects about to be finished, which kind of connect tameness into various pieces of physics. And I will highlight some results coming from a paper with Mike Douglas and Lorenz Schlechter. Lorenz is a postdoc here at Utrecht University. Now, what I hope that you will get from this talk is that, first of all, that you hear already kind of, you get a first understanding what is tame geometry. So at least a rough idea of what is so exciting about tame geometry. And then maybe you also start to see various places in physics where it pops up and why it is so remarkable and powerful. Let me start with an introduction. Well, I start with some sort of very general slide. Well, I think it's fair to say that mathematics is wild, right? Especially when we start studying mathematics or physics, or we learn about analysis, and we learn quite a few wild things about mathematics. In particular, we learn that topologies and maps can be very involved. So in particular, we learn about complicated sets like Cantor sets, where you take an interval and then you cut off the middle third part, and then you iterate this, and then you get really wildly complicated sets. We learn about very complicated functions where you, for example, you have a function which is 0 at all the rational numbers and a 1 at all the irrational numbers. Yeah. So for mathematicians for mathematicians doing analysis, this is of course kind of standard material. But there is a common feature that there is no graphical representation and there's seemingly no geometry behind this. So this is really, seems to be kind of something which comes up in analysis, but not really in geometry. Now, if you then dig deeper into mathematics, you learn about logic, and then things get even more wild, because you hear about Gödel's first incompleteness theorem, and then it's kind of, you realize that there are statements that are even undecidable from a mathematical fundamental level. Yeah. So this is when one starts to think about general aspects of mathematics, and then when we go into physics, one hopes, and maybe one is convinced, that physics should be more tame. Yeah. So there should be something which kind of prevents us from running into all these complicated features which I described. So this is kind of my general motivation from a mathematics side now, but I should tell you how I got to think about this. And this was actually about tameness. And this was actually from a very different perspective. Namely, I was thinking about the question, about one long-standing question, namely, is the number of distinct effective theories arising from string theory finite? So this has been discussed already many years ago, 20 years ago. It was kind of conjectures were made along these lines. And there has been much recent activity to kind of check whether or not this can be true. So finiteness statements about all kinds of physical quantities. And when thinking about specific effective theories, this can be turned into a mathematically clean question. Namely, when you talk about flux compactifications, and I will do that in this talk to some extent, then you can ask the question if certain number of flux compactifications are finite, and then turn this, actually one can show that this is a true statement if I make it more precise, and it can be turned into quite a general mathematical theorem. Now, you might ask, so this is now about finiteness. What does this have to do with tameness? So with the idea that things cannot be too wild, yeah? So finiteness seems to be a yes or no criterion. But what we actually want is we want to have some sort of structural criteria, not just a yes or no criteria. And there are some recent suggestions how this could arise. For example, that suggestion that one can think about finiteness of quantum gravity amplitudes. Then this is much wider applicable than kind of just the finiteness of number statement. But what I will do here in the talk is I actually use the insights which we learned or which we used in the proof of this finiteness result of this theorem in this paper, and claim that this is more generally present in physics. Yeah, and in fact, what we use in this proof is a field of mathematics which you might call Tame geometry, sometimes also called O-minimal geometry. So what is the rough tameness statement? And of course, I will give a more precise meaning to the word tame in this talk. In fact, what one observes after thinking about this tame geometry is that effective theories derived from string theory that are valid below a fixed energy scale have tame coupling function, field spaces, and parameter spaces. Furthermore, what we now start seeing is that if you start with a tame effective theory, or say a renormalizable local quantum field theory, then it remains tame if I include perturbative correction up to a fixed loop order. So actually tameness seems to be even something which is preserved in quantum field theory at the quantum level.
Will you give an example of an effective field theory which is not tame?
Yes.
Okay, great, thanks.
Yeah, I will mention one which is not tame. Yeah. Okay, so just to get us all on the same page, what do I mean by effective theory? You can think of this, or with this tameness statement, what you can think of these effective theories as being given by some Lagrangian. And this Lagrangian, this will have maybe some kinetic term for some scalar fields phi, and the kinetic terms will have a metric here, which might depend on the scalar fields themselves phi, or it could also depend on some parameters, and in general, it will depend on some parameters. Then there can be a gauge coupling function for some gauge field. Again, this can depend on the scalar fields phi and some parameter. And there can be also a scalar potential. So the coupling functions depend on parameters of some parameter space, and they're in scalar fields which live in some field space m lambda. Of course, lambda can also depend on the parameters. So the parameter space actually I can denote by P, and then the field space can change over it. And I give you some examples what you can think of as a parameter space. You can think of it as the number of fields, the webs of heavy fields, fluxes, topological data. So in principle, it could be quite a complicated set, right? It could be possibly discrete, right? And with many components. So what is then now the tameness statement which we observe is that this parameter space and these field spaces and also these couple functions are actually, special Tame sets and special Tame functions. So they are not drawn from a general set of functions, but they have certain special properties, and in particular, the properties which are mentioned in the wild mathematics, they seem to be not present in physical quantities. Now, already as a cautionary remark, any such structure has to have certain features to be possibly true. Yeah. And so what is the challenge, for example? Well, if you think about effective theories, which are defined below a certain cutoff, then you can have a cutoff dependence. Yeah. Or you will have a cutoff dependence in general. And in particular, if you have a scalar potential, which renders some of the fields massive, it can happen that while at a cutoff lambda, your field space takes on a certain form, it can happen that if you lower the energies, some of the fields will be so heavy that you should not keep them in the effective theory. In fact, you should integrate them out. Yeah. And then the field space of the new effective theory, say at energy scale lambda 1, will have a smaller, might have even a smaller dimension. And there could be even multiple new effective theories, right? So it could have potential with multiple minima. Or for example, you could even say that if I lower the cutoff even further, say almost close to 0, what remains is no field space and just some discretum of points. Yeah. And the statement now is that all these field spaces which appear in this whole process of lowering the energy should remain tame. Yeah. And in particular, we will see a feature of tameness will be that it's kind of just a finite number of possibilities, finite number of sets appearing in this process. Okay, so now I have told you quite for some minutes in abstract terms what I want to have, wanted to be tame. Now I should finally tell you what I mean by tame. And so I will try to give you a brief introduction into tame geometry. This is a huge field, so it's more thought as giving you a flavor of the topic. So where does it come from? Well, maybe one way of tracking down its origins, and that's also where the name came from, is to look at a research proposal of Grothendieck, which he wrote in the beginning of the 80s, and it's called a sketch of a program. And essentially, he was arguing, as far as I understand, that there should be a mathematical framework developed for geometers, and which removes some of these pathologies which you can have in ordinary topology. Like, for example, these contour sets are not something which a geometer which would encounter. And as far as I understand, he got these ideas when thinking about moduli spaces of Riemann surfaces. So essentially, he formulated some ideas what kind of properties this geometry or this Tame topology should have. Independently, in logic, there was some development on understanding certain structures, which were called O-minimal structures, and I will define a little bit later what they are precisely, namely a development of the theory of O-minimal structures. And they came from a very different angle. So the approach came from a very different angle. It was part of what is called model theory. And it might be, you might track its origin to saying that after kind of these Gödel theorem, which I mentioned at the beginning, which has undecidable statements in general, that you want to generate a structure which only has decidable statements. Yeah. And this was actually achieved when you think about polynomial equalities and inequalities over the real numbers. If you include the ordering, right? You have to define a symbol which is kind of an ordering in the set of the real numbers. That's what I mean by inequalities, of course. Yeah, and it was shown, I think, very early in the 30s or 40s that this in structure already gives only decidable statements. And now the question was for these model theorists, for these logicians, what are the structures which you can you extend this into something more interesting beyond polynomials? What kind of things can you add in order to keep some of these strong statements about decidability, and but make it richer than just these polynomials? Yeah, and this is where the big breakthrough was made, that now there's a clear understanding of these structures, these O-minimal structures, which have a very well-defined features and many of these interesting properties which logicians like for these model completeness and decidability statements. So what is now the resulting picture? In fact, these two questions came together, and one understood that actually these O-minimal structures provide a tame topology. It's very similar to what Grothendieck had envisioned, right, in his essay. And they give a generalization of real algebraic geometry. So real algebraic geometry would only deal with algebraic polynomial equations, but that's not really rich enough. And also for many applications in physics, we know that not everything is polynomial. And one also realized that it has strong finiteness properties. Yeah. And if you're interested in the subject, I can highly recommend this introduction book by Van den Dries. Yeah, it's a short book. It's also easy to read because it starts at the very basics. And once you are a little bit in the subject, there are online lectures by Jakob Zimmermann, just from last year. And one of the reasons is because this is a very active topic in mathematics at the moment, and I will mention this briefly why this is the case. So what is the idea? The basic idea is to specify the space of allowed sets, which one calls definable sets, and allowed function, which one calls definable functions. And if you have this sort of notion, you can define what is a definable manifold, definable bundles, a whole tame geometry. Now, how would you build up such a structure which has finiteness properties? Maybe the simple situation, and that is actually the main building block in these structures, is that if you think about the real line, these special sets, these allowed sets, these definable sets, are just either a finite number of points on the real line, a finite number of intervals, or some infinitely long intervals, which well, then obviously you just have a finitely many. Yeah. So these are the definable sets in one dimension, on the one real, in the one-dimensional real line. And the idea is to extend this to Rn. And this is horribly complicated, right? Because you want to somehow preserve this structure. So you have to come up with a set of axioms how to extend this to higher dimensions. And you might have some intuitive requirements. So for example, you might ask that whenever you take a higher dimensional set and you project it down to any real line, that you end up only with these types of sets. So either finitely many points or finitely many intervals. Yeah. Furthermore, you want to have kind of like in topology, you want to have this sort of sets closed under finite unions, finite intersections. So if you intersect finitely many sets, you want to have again a definable set. Or if you take the product of finitely many sets, you want to again have a definable set. And in order really that you kind of cover the minimal ground, which is real algebraic geometry, you want to include all the sets which are given by algebraic equations. So this, in fact, is now what one then calls an O-minimal structure. So an O-minimal structure is in fact a collection of sets, of subsets of Rn, which have exactly these properties which I tried to describe. So they are closed under intersection, finite Cartesian products, and particularly coordinate projections, and contain the zero set of every polynomial. And the only tameness assumption is that whenever you project down to just one dimension, you end up with a finite union of intervals and points. Now, the S-definable functions, so now you understand what definable means. So definable always means these sets or these functions are definable in this O-minimal structure. And a definable function is a function whose graph is part of this structure. So the graph of a function is a set, and the set should be part of this O-minimal structure. That sounds all a little bit abstract, but if you think a bit about this, it's actually it's very fundamental in the basic construction, but very powerful as it turns out. So what are examples? So the simplest example of a definable function is a polynomial function. That's kind of by definition, because I take polynomials to be part of the structure. But there are also easy non-examples. So the non-examples are, for example, sine x, right? So if I consider the sine function on the real line, it can never be a definable function. So no matter how to precisely construct this O-minimal structure, it can never be a definable function. Why? Well, because if you project to the zeros, if you just take a line here, then you have infinitely many zeros. And that means infinitely many points on the real line. And as I mentioned here, the tameness assumption is that a function has to project down to only finitely many points. So a sine function, where x is defined over the whole real line, should not be appearing as a coupling function if this tameness statement is true. Now you can go from there and you can define definable manifolds, where you have a definable atlas, a finite atlas, and transition functions among them, which all satisfy exactly these conditions. Now, to give you a little bit a flavor of how powerful this is, let me recall one important theorem, which is not too difficult to prove, is that if you consider a function f, which goes from the real line to the real line, which is definable, so Tame, then you can always split the domain on which this function is defined into finite number of intervals. And on each of these intervals, this function is either constant or monotonic and continuous. And the function can jump at finitely many points. Yeah? So this is how a Tame function looks like. And now you see also why the sine function, another way of seeing why the sine function can never work, because for the sine function, you would have to partition everything into infinitely many intervals. So there are some consequences to quickly list. So every definable function has only finite minima and maxima if it is differentiable. And it has a tame tail to infinity. So since you have to partition everything into finitely many intervals, there will be kind of the last interval, right? In the last interval, everything has to be monotonic and in particular tame. Yeah.
Sorry, can I ask a question now?
Yes.
So how do things like instanton corrections to an effective field theory fit into this? Because those often have cosine and sine behavior for the axion potential.
Right. I will come back to this later on.
Okay.
Maybe also it gets answered in the meanwhile. Let's see. Okay. Now, so the result too, if a definable function is also differentiable, then the first derivative is also definable. Yeah. So definability is preserved after undertaking derivatives, but not under making integrals. So just to show you how powerful this is, actually, it becomes really powerful if you combine it with other properties. So in particular, if you combine definability with holomorphicity, then actually you can show that the function has to be algebraic, so it has to be a polynomial. So every holomorphic definable function is just a polynomial. Yeah. So in particular, the complex exponential is not a definable function in any O-minimal structure. So it's always a bad thing. Now this is kind of the same thing as Jonathan asked, right? So it sounds very weird. Now I introduce something which rules out a thing which we really like and we see in string theory very often, seemingly see very often. But one has to look at it into the details. But before doing that, let me just mention it's obvious that it's not definable, right? Because if you see it as a map from C to C, it has infinitely many zeros, right? Because the cosine and sine appears. Now, what is a way of saving definability? Well, we can restrict the domain of phi. That would be a way of doing this, because then you don't have any more infinitely many series, but you have just a finitely many of these periods of the sine function appearing. And then you have to ask, well, is the sine function or the cosine function at all a definable function? Can it ever be a definable function? And the exponential function is also a question whether or not it can ever be a definable function. And these are seemingly simple questions, but they're actually very, very deep questions. And in particular, there is, in answering the question, one has to realize that there is no unique choice for such a structure. And that the constructing examples for such O-minimal structures is really difficult and took many years of mathematical ingenuity to construct these structures. Yeah, it's very non-trivial. And the way how to do it is you have to kind of explain what are the allowed functions which generate these sets, these tame sets, these definable sets. So let me explain. So the simple structure is the one which is just generated by polynomial equations. So this is the one which I mentioned already. It's maybe also, it's for sure also the most boring structure in some sense. It was also known before. It's generated by the sets which are just given by a polynomial in n variables and then all the unions of these polynomials you have to take into account, and all the projections of these polynomials. And this is called the set of semi-algebraic sets. And this structure is called R-alg. Now this is the one which also had this kind of nice decidability statement, but then a big breakthrough happened. Well, then the first extension of this is to add some analytic function, namely called restricted analytic functions. Then you already get a bigger set, but it's much richer, but it is only including functions which are restricted to some small set, yeah, some smaller set, say from 0 to 1. So like taking the sine function and restricting it to a set, then this would be inside this O-minimal structure, a definable function. If you restrict it, right, the x and sine x. But the big breakthrough came when the logician, so this was all developed in logic, right, by the logicians. And so the big breakthrough came when they realized that you can add the exponential function and still generate such an O-minimal structure. So adding the exponential function is a valid thing to do, and the exponential function can really be added with x going to infinity. Right, so exponential of x is tame, is tame enough to kind of preserve these axioms, and this is a really a deep mathematical fact. And the way how you can think about this is maybe the following: that this is kind of algebraic. This is an algebraic equation, and that means that you here enter the transcendental world. So you suddenly have transcendental functions which are also tame. Yeah. And in fact, what you even can do is you can combine these two O-minimal structure into a really big one, which is called R-unexp, which now contains the exponential and also these restricted analytic functions. So analytic function, remember, always think about it like a sine function restricted to a smaller set, or any analytic function, so where you can have the Taylor series approximating the function, but you have to restrict them onto a smaller set. And in fact, in geometry, it's this O-minimal structure which is all the time there. So this is it's quite remarkable. In fact, if you think about it, even to make the complex exponential with this angle restricted to be in a finite interval, you already need this O-minimal structure, this really rich O-minimal structure. So you see in this theory of O-minimal structures, the game is to make it as big as possible and still preserve these finiteness properties. So this is the difficult part, not to make it as constrained as possible. And as I mentioned, this Rn(x) is sufficient for most geometric applications, and it will be the O-minimal structure which appears in all the effective theories that we will discuss later, and also in the QFT application. Let me mention, there are also functions that are not definable in Rn(x), and functions which you know very well. The gamma function is not definable, the error function or the zeta functions. So, of course, it's very important on which set it is defined, right? If you take it from 0 to infinity, it's not a definable function. So if you have gamma functions in your model, they have to combine in such a way that definability, well, if this tameness idea is correct, then they have to combine in such a way that the combination is actually tame. Now, I told you now a lot about the one-dimensional sets and so on. the real power of the structure comes if you go to higher dimensions. Yeah, so, but this is very well understood. And the big basic insight is that whenever you have a higher dimensional set, you can partition it into finitely many what is called cells. And the finiteness is again very important in this respect. And then you can prove things about these cells. And then what happened more recently, so this is what I said so far is rather old, maybe the 90s. What happened more recently is definability can replace compactness in many famous theorems. And if you replace compactness by definability, you can prove similar things. And then these theorems suddenly become extremely powerful. And they apply to situations which you were not able to apply them before, because before you were just using algebraic geometry, but suddenly you have a framework which kind of flows a little bit in this transcendental world, which has the kind of the exponential function and so on. And in fact, this was used in very recently, just in the last few years, in proposing. Well, the first one is just a proposal; it's not yet published, but proving some of really long-standing conjectures in this field. Yeah. So I just listed a number of conjectures. And so it's really an exciting development in mathematics, which is going on there. Now, let me explain it. Let me come back to the physics application, and let me tell you a little bit how tameness is at work when it comes to the question which I sketched before. So let us now think about a tame field space, which we now know how to define properly. Namely, we say that the field space M is a definable manifold in some O minimal structure. And now we say that the potential, the scalar potential, which depends on some field, is a definable function. So now, at least you should have a rough idea what that means, right? It's kind of, it's a well-defined, its graph is well-defined in this structure. And now if you lower the cutoff, classically what you have to do is you have to integrate out fields. And if you do that classically, you solve the vacuum equations, but the vacuum equations are again a definable manifold. And because the first derivative of definable function is definable, and so this zero set is a definable manifold, and the intersections of definable manifolds are definable because the structure is closed on the intersections and so on. So you see that the vacuum locus is also a definable manifold, right? So it's really closed under the things which we do in physics, at least at the classical level, right? Now, you can even take your functions and put the vefs in, and it still will become a definable, it will remain a definable function. So tameness is classically preserved when lowering the cutoff, but now you might ask what happens at the quantum level, and I will comment on this later on. Now, if I now impose the tameness assumption, I now can rule out wild scalar potentials. For example, what you can easily cook up, and it even appears in some physical models where you even doubt that they are well defined, you can think of like infinite spirals to some point. Yeah. And these infinite spirals to some fixed point, I didn't try it infinitely long, but just kind of, you have to imagine that it continues forever. This is actually never definable. So there's no potential, no definable potential, no tame potential, which can ever generate such a valley, right? And you can see this very easily. You can take a projection through this line, and this real projection would pick up infinitely many points. Yeah, and therefore this would go against the very basic tameness assumption. having infinitely many vacua is also not compatible with tameness. And this is similar to the sine function, right? So I could just take kind of projections here, and then you would see, oh, well, if I have infinitely many minima, this is not fine with tameness. Or you take this theorem, which I sketched, that you have to be able to divide this line into finitely many intervals, and so you can never have infinitely many minima. So many functions do not appear if you assume tameness. And such functions were exactly discussed in this older papers in the early 2000s by Acharya and Douglas, where they said, oh, but wait, if the number of effective theories from string theory is finite, then what do we do if we find such sine functions, and then you have some sort of accumulation points of vacuum? So if you take tameness into account or assume tameness, this cannot happen. Yeah. Now, another interesting thing is that if you look at this recent paper by Tachikawa, where he writes down some two-dimensional quantum field theory with undecidable statements, you can easily check that the functions which he writes down are actually not tame. Yeah. So in fact, he also uses a sine function to get a projection down to the integers. And in fact, these incompleteness theorems, they come because one works over the integers, right, or the positive integers. So tameness is fundamentally incompatible with these sort of suggestions for QFTs, which are, well, with this, at least with this suggestion, with this QFT, which is undecidable. Now I introduced a little bit of what this tameness structure is. Now,
can I ask a question in
yes,
the supersymmetry? So before you go to supersymmetry, so in quantum field theory, we have RG flows where you try to go to zero momentum limit. And there is a question where you can get limit cycles, which can be very funny, where you can have, we don't expect RG flows to do some very funny infinite loop and asymptotically approach the zero momentum where you wouldn't get a CFT. Can you rule out such a funny cases of RG flows?
Well, the problem is a little bit when you say, can I rule them out? Of course, you could say that if I impose the structure, then you could rule them out, right? But so it's not. I cannot answer this question because you have to tell me whether or not you accept that these things cannot happen. So that the structure has to be tame. But
we expect that if I take the zero momentum limit, I get something which has an emergent conformal symmetry, and
right. But you ask an excellent question, and we of course we are thinking exactly about these sort of questions, how to apply it in QFT. So I cannot fully report. So we thought also about the renormalization group, and there things are a little bit tricky. Maybe I can tell you at the very end. But
okay.
But you will. So what I will report in the last few minutes is kind of some partial progress when it comes to loop amplitudes, right? But this is not yet enough to study like the full behavior of the renormalization group.
Okay, thank you.
Okay, so now this is the Tame geometry which I introduced, and now of course I can just say everything is tame. Yeah. So, but I should tell you, is there some evidence that this is at least true in highly supersymmetric theories or in string theory or in effective theories which come from string theory? So let me start with highly supersymmetric theories. And again, I will be using some recent mathematical breakthrough results. And you will see that it's kind of exciting that it just all pops up exactly as one would need it for these cases. So if you have supergravity theories with more than 2 supersymmetries, we know that the scalar field space is actually written as kind of a coset. We would probably call it a coset space. Yeah? In mathematics, you would call it an arithmetic quotient of certain groups. Yeah, but it's called arithmetic quotient if this is an arithmetic group. Now, the nice thing is, very recently it has been shown in this seminal paper that these are actually definable manifolds. And in fact, they have a very nice definable structure in this R-alg. They're even this kind of semi-algebraic definable structures. So this is a non-trivial observation, because you have to construct this finite atlas of sets which covers this manifold. And this can be very explicitly done. So it's even interesting from a technical level. It's very interesting. Now, the coupling functions which you have in these higher supersymmetric theories, you probably know they don't involve exponentials if you have a lot of supersymmetry, right? Because instant-on corrections are not allowed because of supersymmetry. So they are roughly polynomial things. And in fact, what we are now showing is that there are good arguments that they are definable in R-alg. Yeah, so they are also definable functions. Now, when it comes to the parameter space, that's the most tricky thing, because now I have to tell you what kind of parameters am I allowed to choose to define my supergravity theory. And in other words, for example, how many choices do I have to fixing this group G, right? And in principle, you have infinitely many choices if you just think about supergravity. But if you think about string theory, there's actually good indication that that the rank of the gauge group is bounded from above, right? So that's what we find in construction in F theory. There seems to be always kind of an upper bound on the rank of this of these groups, or the upper bound on the number of fields. And so discrete infinite sets would be never definable, but kind of at least within string theory, there seems to be always a finiteness statement which cuts this down. So you see, these three things are actually nicely to check in these higher supersymmetric series. Now let me lower supersymmetry a bit, and let's go to n equals 2. Then I have less supersymmetry. And one example where we find this in string theory is when you take, say, type 2A or type 2B on a Calabi-Yau manifold, a Calabi-Yau threefold. Then we know that the theory classically, the theory has no scalar potential, and it's a well-defined background and so on, and we can compute the 4-dimensional theory if you take a threefold. And then you see that the field space is the complex structure moduli space, so the deformations of this manifold. This is a really complicated space. And we also know that the theory, at least the vector sector, is defined in terms of a Kähler potential and some gauge coupling function. So now imagine that you have this effective theory, which has n equals 2 supersymmetry, and you ask the question, is this now a tame theory? Is this has this definable coupling function and definable moduli spaces? Well, to proceed, you have to realize that in fact, this scalar potential and coupling function, they're all computed from something which is called periods. And these periods are certain integrals on the manifold, if you want volumes in this manifold, which change over the deformation space. And another remarkable result of this paper is that in fact these periods and also the Hodge star operator are in fact definable functions in this very in this large O minimal structure which are introduced R and exp. So you see, you need the exponential. Maybe you know why one needs the exponential. But of course, we know in n equals 2 there are instanton corrections. So this was also something which Jonathan said. You have instanton correction, so the exponential should be there. And you need the analytic part here, for example, because you have the sine function appearing from this instanton correction. But in string theory, you actually know that the angle which appears in the instanton is always on a compact space. So it's not an infinite line, but it's kind of something compact because of monodromy symmetry, because of these monodromy symmetries. So there's an actual symmetry which kind of compactifies the infinite direction, which would be bad for tameness. It's very fascinating. So it's kind of a connection between having these global symmetries and the fact that this kind of then ensures tameness. So what can you then check is that in fact the Kähler metric and the gauge coupling functions are in fact tame. So they are definable in this R on X. I should note that these period maps, they have parameters. Yeah? For example, for mirror symmetry, we know that they depend on the intersection numbers. And whether or not this parameter space is a tame parameter space is a very non-trivial question. Namely, it depends on the finiteness of compact Calabi-Yau manifolds. So if you have only finitely many Calabi-Yau manifolds, you would have only finitely many possible intersection numbers. And then these parameters in the scalar potential and in this gauge coupling function would just be a definable set. And it's widely believed that the set of compact Calabi-Yau manifolds is finite. Now, you might find this disappointing because I tell you, so far I only told you that the field spaces which come out of string theory, at least on these examples, are definable, are tame. I told you that the coupling functions are tame, but I never showed you an example where the parameter space is tame. Yeah. And this is actually kind of what we find in these flux compactifications. In these flux compactifications, you have a parameter, and the parameter is the flux. And it's discrete, and it lives on a lattice. So it's something really, really non-definable, right? It's something discrete and infinite. So if you have a background flux, if you couple it to gravity, if you are in a compact manifold, you have in this type 2B or F theory flux compactification, you have this tadpole condition, which you have to impose for consistency. And it is very important for definability, for tameness, yeah, as we will see in a moment. And then if you compute the effective theory, it has a scalar potential, and the vacuum condition is some self-duality condition. So I don't want to describe the details of this. People who know this will recognize immediately what I'm talking about. Now, if you fix the flux G4, then the scalar potential is actually definable in R and X. So it has finitely many minima and minima, yeah, or many minimum loci. Yeah, it could be flat direction, but finitely many flat directions always, or finitely many loci. Okay, so this is not too hard because it follows from the fact that everything in this scalar potential is definable. The Hodge star is definable. But what about if I don't fix this parameter? Is it still tame over the parameter space? And this is kind of the non-triviality in this theorem which we prove. And in fact, the tadpole helps. And what one shows is by using some lattice theory, one shows that if you impose the tadpole constraint, then the fluxes, they split into finitely many orbits. The orbits can be contain infinitely many fluxes, but only finitely many can appear. So finiteness is related to compactness of Y4 and so to the coupling of gravity. And what we then show is a much more general theorem, namely about the self-dual fluxes, is that they are just give as a vacuum locus a definable space. And in particular, there are just finitely many choices. So this solves this long-standing conjecture if the number of flux vacua for a fixed Calabi-Yau manifold is finite or infinite. So it's a very general theorem. Its proof uses all kinds of non-trivial tricks, in particular this definability of the period map. And it's actually a generalization of a very famous theorem in Hodge theory about Hodge classes, which was proved in the mid-90s and which is kind of still viewed as the strongest evidence for the Hodge conjecture. So it also has a finiteness statement, and we are able to generalize this finiteness statement to much more general classes than just Hodge classes, namely to the self-dual classes. Now, this ends my discussion in string theory. So I have shown that in flux compactification, I even find that I have definable, so I have tame parameter spaces. Namely, if I impose the tadpole constraint and I'm really close to the true minima of, like the really well-controlled minima of the theory, everything is tame. So this is the first tameness result of, in this context where you have a parameter space, a discrete parameter space. Now, finally, let me explain a little bit of evidence for from perturbative quantum field theory. Now, I shift gear. I start with a general local quantum field theory and look at loop amplitudes. Yeah. Such loop amplitudes, they can depend on momenta and masses. So masses running in the loops and external momenta which satisfy some conditions. And this amplitude can be now understood as a map from the space of momenta times the parameters, which are masses and vertices. Yeah. Just in the typical Feynman integral sense. And now what we can show is that all these maps are actually definable. So every L loop amplitude in such a QFT is a definable function. And the basic idea is simple to explain or just to sketch. It's we decompose an amplitude into Feynman integrals. So this is, you know very well. But what is maybe not so well known to many people is that there is a nice and deep relation between Feynman integrals and period integrals. So these periods which appeared before appear also in Feynman integrals. And you construct an auxiliary geometry, and then you can associate to each Feynman integral, you can associate some period integral. And this can be made very concrete. And I can refer you to the review book of Weinzel for details. And now if you do that in detail and go through the various steps, what you can then use is that the pure and the mixed period mappings are in fact definable in RNX. Oh, and there's a typo here. So this was just proven very recently in 2020, and I've also forgot to include one of the authors, Prunebarb, I forgot to include. Sorry for this. So this is just a 2 years old result. And then we can check that all the maps involved in this construction are definable, and you show the definability of this, these Feynman integrals, and therefore of the amplitudes. Yeah. So you have to keep always finiteness at every step. That's very important. Okay, and then to close up, I just have like one slide Well, this sounds very exciting. I'm extremely excited about this. So I have a lot of projects on this in various directions. And one way of thinking about this is that, well, maybe we can just say there is a tameness conjecture, and everything which is fine with quantum gravity, at least with string theory, is actually definable. So every effective theory just has definable coupling function and so on. And if you want to refine this, you can make the O-minimal structure explicitly present here. And this is exactly what comes out from every example which I have looked at so far. So this brings me to the conclusion. So Tame geometry and O-minimal structures seem to be omnipresent in effective field theories. There are strong finiteness properties. It's general enough to talk about non-supersymmetric situations. I talked about just general QFTs. So you could say it's a structure for the real world, where real could mean over the real numbers. And its highly non-trivial finiteness theorem gives evidence, but of course this is kind of in a certain corner of string theory, so it's very important to collect more evidence. One of the pieces of evidence is what we are developing at the moment, QFT at n loops. And of course, we also think about QFT with non-perturbative corrections and so on. And we show that if you combine this conjecture with other conjectures, then you find quite remarkable statements. Okay, this is the end of my talk. Thanks a lot.
Let's thank Thomas, and then we can take questions.
Dave's got a
Please
question.
go ahead, David.
So you argued that n-loop amplitudes are finite, or definable, I should say, but really we want to add them all up, and that's an infinite number of things. So what about the full perturbative QFT?
Yeah, this is a very good question. So in fact, you're absolutely right. So, and of course, that's why I formulated things as I formulated them. So if you have an infinite number of integral definable functions, you add them up, it's by no means clear that the answer will be definable, right? That's kind of against the whole idea of the structure. So indeed, in QFT, it's also, it's not clear if you really want to sum the whole the whole series by just computing individual Feynman integrals. So if you want to have an answer for the full structure, for the full sum, this might involve some non-perturbative corrections and so on. So it might involve kind of the whole series as a kind of a non-perturbative way of looking at things. In fact, we know that if we sum just some Feynman integral, it can converge and then kind of diverge, right? If you add more and more loops to the story, right? And so how do you overcome this? So what we are thinking about is, well, maybe there are some examples, and of course there are some examples where we know the whole sum. And then the question is definability preserved in these examples where we know the whole non-perturbative, like exactly solvable models? Yeah. So you're absolutely right. So the argument doesn't go like, I do it at n loops and then sum up everything. So the full answer is more involved than just summing up. But it's very interesting because that kind of hints to something nice. Yeah.
Can I have a follow-up to this question?
Yes, please.
So, but it still makes sense to talk about, you know, the perturbative part of the amplitude that you add up without even talking about the non-perturbative. People still think about that, for example, in trying to prove, you know, that n equal to 8 is somehow finite, at least perturbatively. But if you try to sum up all the loops, it's finite. Are you telling me that there could be some sort of interesting cancellation structure that I could look for to try to understand between non-perturbative contributions and perturbative contributions?
What I'm saying is I'm not saying that it's necessary. So it's not true that every infinite sum of definable function is necessarily non-definable. It could be that you have an infinite sum of definable function, and this just gives you another definable function, but it's just not guaranteed. So that's what I'm saying. So if you believe in tameness, and maybe one should believe in tameness because it's so, well, I don't know, because it's related to this decidability questions and so on. And so that seems to be something fundamental and deep to believe in. Then you could exactly ask what you are asking. Well, take examples where the individual, where this actual sum would be non-definable. And then you say, well, but I believe in tameness. So what could possibly make this infinite sum tame? Well, then it should be the non-perturbative part. So indeed, you're right. So you can hope for that the non-perturbative pieces kind of cancel some non-tame parts in this just naive sum, if it is non-tame. Yeah, if you, yeah. Is this clear what I'm getting at?
Yeah.
So it could very well be that if you say n equals 4 is finite, and even if you sum over all the loops, that is not necessarily a contradiction to what I say, right? It could be also that the whole sum is still definable, still tame. But then you have to show it directly. You cannot show it by showing that individual pieces are tame.
Okay. Let's thank Thomas one more time, and then we can turn off the recording.